Okay, here's a couple homework problems from chapter 7. Okay, so this one has, they give you a little picture, but I drew a couple other pictures. Okay, so they tell you that you have a block at the block of mass m, there's some spring constant k, at the equilibrium position, x equals 0. Okay, then it's pulled out to here. Pulled out to 5 centimeters, and they say to do that and hold it there, it takes 360 newtons of force. That's this picture. So start at rest. In this picture, I'm holding this thing here, and it costs me that much force. So if the block isn't moving, then the 360 newtons is balanced by the spring force. So essentially from here to here, it tells me that the spring force is 360 newtons when it's stretched 5 centimeters. So that allows me to say, oh, well, Hooke's law says the spring force is kx. So the spring force is 360 newtons. So in magnitude, spring force is kx. Solve this for k. So essentially this section here, that to there, gives me enough information to find the spring constant. Okay, so now we have the spring constant. So now it says you pull it out to 13 centimeters. Okay, so you bring it out here to 13 centimeters. Okay, now you let go, and they want to know the work done by the spring as it moves from 5 to 4. So they want to know the work done by the spring as it goes from that point to that point. Okay, so, and we showed in our notes the work done by the spring. You have to integrate the spring force. That's an S. You have to integrate the spring force. Okay, so I'm integrating minus kx. Remember, the spring force is minus kx from x initial to x final. So I just do this integral. Okay, so the minus k comes outside. I'm integrating x. Okay, so just be careful of the plus and minus signs. So for part A, it's going from the 5 centimeter to the 4 centimeter mark. So make sure you read through that carefully. So they want the work done as it goes from that point to that point. It's moving to the left. So my initial is the 5, my final is the 4. It's moving to the left. So I just put in my x final there and my x initial there, and I just calculate the work done. And then I do the same for B. Part B, they want the work done as it goes from 5 to minus 4. So in the picture, that would be from 5 somewhere out here to minus 4. Okay, so if that's the case for part B, my x final is minus 4, and my x initial is still 5. So I put that in, okay, that gives me the work done by the spring. And now they just want it from that same 5, but now further to the left to minus 5. So in the picture, it's going from here, oops, that was the 5, and it's going out to minus 5. So from the information they gave us, x initial is 5, and it's moving off to the left. Whoops, x initial is 5, moving off to the left to minus 5. So I go back up to here. Okay, x initial is still, oops, wrong one. X initial is still 5. Now my x final is minus 5. And the same for D. X initial is 5, and now they just want to keep going all the way over to the left to minus 10. Okay, now we'll see this in a later chapter. We do oscillations, but if you let it go here at 13 centimeters, this thing is going to go all the way over to minus 13. And it'll oscillate back and forth with an amplitude of 13 centimeters. We'll see that in a much later chapter. Okay, number 10. Okay, so I drew a picture here. So they give me a force. Okay, now I use P for the force, and then later I realized I shouldn't have used P because we're going to use P for power. Okay, so I'm just using, there's a pushing force P. Here's my x-axis. And then this isn't drawn to scale because if there's a force acting, okay, this thing's going to accelerate, so it's going to be like your dots. they get further and further apart. So I kind of showed that a little bit. So this is time 0. That's after 1 second, 2 seconds, 3 seconds, 4 seconds, just like your dots. Okay, they're getting further and further apart. Okay, so they want to find the work done by the force in the first second, the second, and so on. So let's do part A first. Okay, so it helps to draw this picture. So if this is time 0, 1 second, 2 seconds, 3 seconds, this interval here, that's the first second. They want the work done by that force P during the first second. Well, definition of work is force dotted into the distance. Well, I call the force P. So it's the force times the distance x, which we have to find, times the cosine of the angle between them. Okay, but the angle between P and x is 0, and cosine of 0 is 1. So I need to find how far it goes from A to B. Now you're back to chapter 2. Okay, so I did kinematics, initial velocity 0. Okay, so that gives me my x. Instead of writing as delta x, I said, okay, delta x is final minus initial. Initial coordinate is 0. Okay, so that gives me x final. And then I need a. Well, Newton's second law says F is equal to ma. So if I solve that for a, okay, oops, if I solve it for a, and my force is P, if I solve this for a, acceleration is the given force over the given mass. So over here, I had work is the force times the distance. Here's my force. There's the distance. But I put in what A is. A is P over M. And I put that in right there. That's A. Okay? So I have the P squared, T squared over 2M. Okay? And I put in the given force P. Okay, it's during the first second, so that time is 1 second. Okay, because it's only traveled for 1 second. And then just to make sure I check the units, I took my Newton. Okay, I wrote a Newton. A Newton is and it's squared, so it's a kilogram meters per second squared, but it's squared. So I have kilogram squared, meters squared, and second squared squared. So I wrote the seconds squared twice. Here's an S squared, I wrote that, and then kilograms on the bottom. And if you cancel those out, you wind up with joules. So indeed, you get the correct units. Okay, part B, they want the work done by the force during the second. So in my picture, that's the second. I'm going from B to C. Okay, so it's the same thing. Work done is the force P times the distance. So I need to find the distance from B to C. So that's what I did here. I need to find the distance from B to C. So what I did is, looking back at my number line, I said, okay, how far is it out to point C? And I know how far it is to B. And then I subtract that distance away to get the distance between B and C. Okay, so here's that part. So I want to find the distance from B to C. I use kinematics. Okay, acceleration is force per mass. That's from above. And then the time it took to go from A to B. Whoops. Yeah, the time it took to go from A to B, that was 1 second up in the picture. So that's delta x from A to B. And then from A to C, the time it took to go from A to C, that's 2 seconds. Okay, so right here I put in 2 seconds. So that's the time, that's the distance to go from A to C. So I took the whole distance from AB to C, the whole distance from A to C, subtracted the distance from A to B, and that's the distance I want. Okay, so I just did that minus that. So this gives me the distance between points B and C. So now the work done by the force from B to C is that force times that distance. So that number goes right there. And then it's the exact same thing. Find the work done during the third second. So that's why it helps to have the picture. Okay, so here's my third second. Okay, so I need to find my delta x CD. So I go down here. Okay, so the work done during the third second is the force times the distance from C to D. Okay, so use kinematics to find the total distance out to point D, and then I subtract away the distance from C, and then that gives me the distance from C to D. Okay, so I went from the whole distance A to D, right there, distance A to D. On the picture, it's 3 seconds from start to point D. Okay, I found that. And then I already had the distance from A to C from the previous section up above. So now I have the distance from C to D, same force. I just found that. And that gives you the work done by that force going from C to D during the 3rd second. Okay, now part D, they want the instantaneous power due to that force at the end of the 3rd second. So that's why the picture helps. Here's the end of the 3rd second right there. Okay, that's at 3 seconds. So I need to find what's the velocity, because the instantaneous power, and I'm using that P for power, is the force dotted into the velocity. So that's part D. Okay, so when I do part D, because I by accident already used the letter P, so I'm using that kind of P for the power. Okay, so I want to find the instantaneous power at point D. So the force dotted in the velocity. Well, I know the force, that's my 4.6 newtons. But I need to find the velocity at 3 seconds. So back to kinematics equation 1. Okay, so initial velocity is 0 where we start. Acceleration is still force per mass from Newton's law. The time it takes to go from rest to D is 3 seconds. So this gives me the velocity at point D, and then my instantaneous power, okay, at point D due to that force is the force dotted into the velocity, and that gives me what they asked for. That gives me the instantaneous power due to the force at that point. Okay, you work out the units, it comes out to newtons times seconds. Okay, oops, not newton seconds, that's a newton, and that's meters per second, and a newton meter is a joule, and a joule per second is a watt. Okay, number 14. Okay, so here's a spring of mass. Okay, that's my relaxed position. So, and they give you the spring constant. Spring constant right there. So they want to know how much work does the spring force do on this mass when it's stretched from its relaxed position A to B. Then they want to know how much additional work is done by stretching it from B to C. Okay, well, straightforward. Work done by a spring, I integrate the spring force. Okay, so there's my spring force. Remember, the spring force is minus kx. Integrate it from any initial place to any final place. So this integrates directly to that. Okay, just integrate that. Okay, we did that in the notes as well. That's a 2. Okay, and careful the minus signs. Okay, so for part A, I'm just putting in my x final and x initial. So my final point is 7.6 millimeters, x initial 0. That's done. Okay, and it makes sense the work done by the spring is negative because the spring force points backwards while this thing is moving in that direction. Definitional work has a dot product. Angle between those two vectors is 180. Cosine 180 is negative, so as we expect. Okay. Oh, whoops. And then for the spring constant, they gave it to us in newtons per centimeter. So I had to convert that to newtons per meter. Okay, and that's what I put there for the spring constant. Okay. Part B, now I'm going from B to C. Okay, so again the work's going to be negative because spring force points backwards and I'm moving in that direction. Okay, so part B, whoops, I'm using this expression here, okay, integrating the spring force, and my final coordinate is my 2 times that, because it says it's stretched an additional 7.6 millimeters. So my final x is 15.2, initial x is 7.6, that goes up in there, and sure enough, I get the work done is negative.